So we started off by saying that inductors were circuit elements and they were important because they could store energy. Let's start to think about that energy storage. And our first step to finding the energy storage, we'll talk about the power of the inductor. So the electric power of the circuit is equal to P. We'll just put elec on there for electric power. And we know that power is equal to I times potential delta V. Potential for the inductor, we label that delta V with an L on it, L for inductor. Now let's put in that we know that the delta V for an inductor is minus inductance times the change in current over the change in time. Okay, one last step and we'll put that all together. The electric power is equal to minus L times I times dI by dt. Now, what does it mean that this is negative? The power is negative because a circuit with increasing current is losing energy. That energy is being stored in the inductor. It's going into the inductor. So that's what it means that it's negative. Negative because energy is being stored in the inductor. So if the energy is being stored in the inductor, that means the power of the inductor is positive. So the power of the inductor is equal to negative power of the electric circuit. So it comes out of the circuit into the inductor. So those guys are equal and opposite. Let's also remember that power is energy over time. I suppose change in energy over change in time correctly. The kind of energy we have is potential energy. So the power of the inductor is the change in the potential energy of the inductor. We'll call that UL with respect to time. And that's equal to the negative of the power of the circuit, which we said was minus L times I times dI by dt. The minus times a minus gives us a plus. Okay, we'd like to solve for the potential energy of the inductor. Let's integrate both sides with respect to time. That gives us du of the inductor equals L times I times di. Okay, this is an expression we can solve. Let's integrate both sides. This slide is a bit full, so we'll just go on to the next slide. So let's integrate both sides. On the left side, we'll do the integral of du. We'll go from 0 to UL. And then on this side, we've got the integral from 0 to I, L times I times di. This is definitely an integral we can solve. So the integral of du is just U. So UL, potential energy stored in the inductor, is the integral from 0 to I times L times I di. L comes out front, that's a constant. The integral of I di is I squared over 2. That's evaluated at I and 0. So L times I squared over 2. So our result is that the potential energy stored in an inductor is UL equals 1/2 L times I squared. Potential energy stored. Now, where is that potential energy stored? It's stored in the magnetic field of the inductor. This feels like a good place to remind ourselves of the result we had for a capacitor. For a capacitor, we had that UC was 1/2 times C times delta V squared. So the potential energy stored in the electric field of a conductor was 1/2 times the capacitance times the potential squared. Okay, those are two pretty important results. And it's good to see that they're similar because they are actually pretty similar devices. Okay, what else can we do with these expressions? Can we find an alternate way to write down the potential energy of the inductor? Let's try that on the next slide. To find an alternate expression for our potential energy, let's fill in what we know about L. So L is the inductance. When we talked about a regular solenoid with a round solenoid, we see that L was equal to mu naught times n squared times pi r squared over L. So this was for a round solenoid. Turns out this is true even if your solenoid is not round. If your solenoid has some other shape, then it's mu naught times n squared times a over L. So that's for round, this is for general. On the bottom there, that should be L, not another a. Okay, so the inductance of an inductor depends on the number of coils and the area and the length, just like a capacitor depends on the area and the plate separation. So let's put this in our expression for the potential energy. We get UL equals 1/2 times the inductance, mu naught times n squared times A divided by L times I squared. Let's just sort of multiply that out without all the brackets. So we get mu naught times n squared times A times I squared over 2 times L. And the next thing we can plug in is we know the magnetic field of a solenoid also depends on the number of coils and the current. So let's write down that expression. So the magnetic field inside a solenoid is mu naught times n times I over L. So let's use this to get an expression for n squared times I squared. N squared times I squared equals b squared times L squared times mu naught squared. Oops, divided by mu naught squared. Sorry, a little bit of bad algebra there. Okay, so what we're trying to do here, our goal is to get an expression of the potential energy. We said the potential energy was stored in the magnetic field. Let's get magnetic field in our equation. That's the goal here. Okay, so we can replace n times I squared with b squared L squared over mu naught squared. So we've got mu naught times A over 2L times b squared L squared over mu naught squared. Okay, I think we can see a little bit of cancellation here. We've got a mu naught on top, that cancels with one of the ones on the bottom. L squared on top cancels with an L on the bottom. And then we have our final result. The potential energy stored in the magnetic field of the inductor is 1 over 2 times mu naught times b squared times A times L. Okay, this is kind of interesting. A times L is the volume where the magnetic field exists. So the potential energy stored in the inductor depends on the size of the inductor and the magnetic field. Okay, and that's a similar result that we had for our capacitor as well. Let's see. So this is true for any magnetic field as well. So this is the energy stored in any magnetic field. The next thing we can do is we can talk about energy density, which is energy over volume. To find our energy density, we'll just remember that energy density is energy divided by volume. So the energy density of a magnetic field is the potential energy divided by the volume. The volume is the area times the length. We see that that's 1 over 2 mu naught times b squared. So the energy density of a magnetic field is mu, so this is a little u, B. The potential energy is a capital U. The energy density is a little u, a lowercase u, is equal to 1 over 2 mu naught times B squared. That's our energy density. So let's just summarize our results here. So for an inductor, we had that the potential energy, UL, was 1 over 2 mu naught times A times L times B squared. And the energy density stored in a magnetic field was 1 over 2 mu naught times B squared. And our result for a capacitor, those were all similar results. The potential energy stored in the capacitor was 1/2 times C times delta V squared. And you could get alternate expressions just by using C equals Q over V. And the potential energy stored in the electric field was 1/2 times epsilon naught times E squared. Let's do an energy example next. We have a 100 millihenry inductor, so L is 100 times 10 to the minus 3 henries, whose windings have a resistance of 4 ohms. So in this example, the inductor doesn't have a zero resistance. It has a resistance of 4 ohms. That's a pretty small resistance compared to typical resistors in circuits, but sometimes it's not zero. It's connected across a 12-volt battery, so that's the potential put into the circuit, 12 volts. And that 12-volt battery has an internal resistance of 2 ohms. What is the energy stored in the inductor? Okay, let's draw a circuit first because it helps to visualize what we're doing here. So our battery has a positive and negative terminal, and it also has a little internal resistance. Okay, so there's our battery. You can even put that inside of a box if you wish, just to remind yourself that the internal resistance goes with the supply of potential. And then we come to an inductor, which is a set of coils, looks like this. And our inductor has a resistance R. We know that current is going to flow through this circuit. Our current is not given, so we're going to have to find our current. After we find our current, we should be able to find our energy. Okay, how are we going to find our current? Let's do Kirchhoff's law. So if we draw a loop around our circuit, we apply the loop rule, we know that the potential increase is due to the battery, that's epsilon. We get a potential decrease across the internal resistance, and we get a potential decrease across the inductor. Oops. So we got our increase due to the battery and the drops over the two resistances. The net potential has to be 0. So we can solve for our current. It's the potential divided by the two resistances. Our potential is 12 volts divided by the sum of the resistances, which is 2 ohms plus 4 ohms. I'm going to lose sig figs here so that I can keep my units. And 12 over 6 is 2 amps. So the circuit has a current of 2 amps flowing around. Okay, let's find our energy next. So the energy stored in an inductor is 1/2 times the inductance times the current through it squared. So we've got 1/2 times 100 times 10 to the minus 3 henries times 2 amps, and that 2 is squared, gives us a total energy of 0.200 joules. That's the energy stored in that inductor. Here's an example for you to try as a homework problem. It's pretty much just a plug and chug, so I won't do it in a video, but I will post the solution.